Welcome to our GTC virtual tutorial on modularizing natural language processing. This talk will be presented by Zhengzhong Liu and Zecong Hu. The slides are also contributed by our colleagues Zhiting Hu and Eric Xing. We are from Carnegie Mellon University School of Computer Science. NLP has empowered a lot of applications, some of which are particularly useful in our daily life, such as machine translation, chatbots, and information retrieval systems that have certain ability of question answering. Applications also include speech recognition and text analysis, who can identify the sentiment of a text. We have also achieved remarkable success on certain benchmarks. For example, on Squad, a question answering dataset, NLP models have created superhuman performance just a couple years ago. Similarly, machine translation have also achieved such a performance on some particular dataset. This is very inspirational. However, they are still on benchmark datasets only. What we really want to ask here is whether current NLP systems are well positioned for complex real-world problems. Let me share with you the following. We, as researchers and engineers, research labs, and companies, have been working a lot with application areas of NLP. And we find that NLP problems, especially put into real-world context, can be really difficult. For example, here is a problem that we recently work on, which is to help the healthcare industry to provide efficiency and quality in the clinical practice. In this kind of problems, there are text data of different content in heterogeneous forms. For example, some of them are more structured in tables, some of them are not. Naturally, there are also other signals beyond text, such as radiology images and genetic sequences. For example, we are asked to produce medical reports for patients based on their radiology data and image, and this whole process has to be integrated into a doctor's workflow. That means simply having a standalone simple program that labels the image is not going to be adequate. Instead, what you really need here is a full pipeline of solutions which understands the images, the text, and accordingly generate human comprehensive descriptions and reports. Such a pipeline would include diverse components. For example, text extraction from historical human written reports, use OCR, and then we need to do a lot of transformations and cleaning to get the data that's ready for standardized modeling and preprocessing. And then we might want to augment this data with different labels, external knowledge, visual and semantic features. Afterwards, we want to do modeling and learning with sophisticated algorithms supported by underlying machine learning modules. And to truly integrate the system into a doctor's workflow, you need to interfaces that present the results, do a lot of text analysis, and highlight the key information to assist doctors for comprehending the generation of analysis results. In this interface, you can see example of critical information instructions such as symptoms and medications. Here is a snapshot of our architectural diagram of a full solution deployment, in which you can see a lot of components that are interconnected, interact with each other. You may ask me, why bother? After all we have done, we have tremendous progress in the past decades in machine learning and deep learning, where more and more powerful models have been rolled out and can achieve a lot of things. We have for sure seen the development of giant neural networks with increasing number of parameters, such as ANSLab and ResNet for image classification, AlphaGo, the world's most powerful Go player, Transformer for machine translation, BERT for text representation, and GPT-2, which is a giant language model for text generation, and finally Mila, a chatbot with 2.6 billion parameters. These models created remarkable results on many tasks, such as visual, text, and game domain. They are very good models, however, they are just increasingly large black boxes of neural networks. The question is, are single giant models enough? Even with all these remarkable results, can this giant model enough to solve real complex problems? Can we just dump in whatever data to learning machines to one end and expect to magically get a model or solution on the other end? Such black box single component treatment suffers from many problems. First, explainability. Are the intermediate results produced at each step? Many applications demand such kind of transparency of data. We need to know what the model is truly doing, but not hoping it to work in a miracle way. Next is debugging and maintenance. It is really hard, if not impossible, to know why the model breaks. The experts have no clue here. Next one is about upgrade. Imagine what if a new tokenization method is invented? How can you upgrade your solution by just replacing the tokenization part, but keep the other components unchanged? With a big single model, it is very likely that you cannot do that. The whole thing has to be retrained again. And with larger models, it's very clear that scalability is an issue. You might have memory and computational issues. From our own experiences, single giant models are inadequate. They are far from being able to solve real-world complex problems, such as the ones we just saw in healthcare. So, how can we really move the process of developing NLP solutions into a more disciplined and systematic methodology? What we really need here is modularization and standardization. As in the aviation industry, we build an airplane by modularizing the whole thing to repeatable building blocks, and then standardize each building blocks as well as the interfaces between the blocks. The standardization enables us to assemble components in a very systematic way. This ensures repeatability, reusability, and gives us control over the cost, time, and quality. The question being asked here is not just a research problem, it is actually a very critical and economically sensible engineering problem. This leads to the tutorial. Here's the agenda. Instead of focusing on building fancy models, here, we instead are going to share with you a systematic view of NLP, in which we decompose NLP into building blocks to see what they are and how they come together to produce complex solutions. In particular, we present in a top-down manner. We'll first do a quick overview of the landscape of NLP tasks and problems to provide some background. And then, starting from the highest application level, we will see how one can decompose an application into a pipeline of diverse components. We will present a standardized view of building NLP pipelines, where each component has its own standardized interface and can be assembled in a flexible way. We'll also present the actual implementation of such standardized view, which is a toolkit called Forte. After that, we'll continue to open the black box of each individual components in the pipeline and dive deep in modeling and learning level. We will present a perspective of what we call Composable ML, which decomposes ML models, architectures, and learning, and then enable building NLP models just like building Lego. First, let's go to the natural language processing overview. So what is NLP? Informally, NLP is about interacting or processing human language using computer. Broadly, NLP contains many fields such as speech processing, information retrieval, text analysis, or speech synthesis. Today, we'll focus a little bit on the narrow part called text processing. In general, text processing has roughly three main areas. Language understanding, which is the task of understanding the semantic of text. Text retrieval, which is the task of retrieving information from a large text corpus. And language generation, which is a task to create new text using the computer. The task of language understanding can be further divided into many different levels of tasks. Roughly, language understanding can be divided into 4 levels, which is known as NLU pyramid. On the lowest level is morphology, which studies the change in different forms of words. On the higher level is syntax of the sentences. On the third level is to understand the semantic of the text. On the highest level is the pragmatics, the way that people use language beyond semantics. Morphology is the study of word forms, how they are formed, and their relation to other words in the same language. While morphology analysis may be unfamiliar to some of you, there are some very frequent morphology tasks such as streamline and lemmatization, which convert the word to their base form for easy language processing. On top of morphology, we have syntax analysis. Syntax are the analysis of sentences, the structure of sentences. Syntax analysis are normally done in the form of parse trees. This is an example of what we call dependency parse. On top of syntax analysis is semantic. Semantic tasks are to find the semantic meaning of text. For example, name entity recognition is to find semantic related units of names. Semantic role labeling is to find the semantic relation between verbs and their participants. Discourse parsing is another type of semantic task, which is to determine the logical structure of a document and finding the relation between document units. Referencing is another semantic task, which is to find text bands that refer to the same underlying entity. Another type of semantic task is entity linking, where you want to find out how text bands are related to background knowledge bases. On top of all this layer, we have pragmatics. Pragmatics is the subfield of linguistics that studies how context contribute to meaning. For example, we need to talk can have very different meanings given different contexts. After language understanding, we still have text retrieval and language generation. Text retrieval or information retrieval is to find relevant documents based on the user query. Some typical IR tasks are search and re-ranking. Text generation is a task for creating text from a program. Typical text generation tasks include machine translation, which creates the text in the target language, or summarization, which creates text in a succinct form, or dialogue responses, which create text to respond to user dialogue. Next, we will talk about how to modularize NLP pipeline. NLP tasks are very complex. You can see we have so many different tasks, so many different stages, and so many different levels. However, real-world applications are more complex. In the following hypothetical scenario, a German-speaking user wants to find some good actors, and we have a corpus of English movie reviews. What should we do? So here is one possible solution in the form of a pipeline. We need to have the reader and then translate the German text into English. Next, we need to create appropriate queries and then run on the backend information retrieval engine. After getting the information retrieval results, we can analyze the text to find actors. For example, in this sentence, we find 2 actors. Now, we can link these mentions to the backend knowledge base to know more information about these actors. And then we might want to use a sentiment analyzer of the retrieval reviews to find the positive ones because we're looking for good actors. With all these information, we can now construct an answer and create a response. So this is actually the expected pipeline. The pipeline is already very long, but real pipelines are not only long, they're more complex. This is the pipeline that might actually look like. First, the raw text need to be fit into different types of NLP system to do the analysis. For example, entity linker need the raw text and the output of NER. We also need to convert the formats between different systems. To make the final decision, the response creator actually need to have access to all the information of these analyzers. This means we need to write a lot of glue code to connect the components. And the glue code is everywhere. The problem is that these processors do not speak the same language. Another problem is that we have such a complex system, such a complex pipeline with many different types of processors. How can we fit them all into a GPU? How do you fit the elephant into the fridge? Our solution here is to decompose the big elephant into smaller elephants and to put each elephant into the fridge at a time so that we can avoid the computation issues. This requires a good pipeline system. So what is a good pipeline system? Here are some good properties of a pipeline system. I will go into the detail of each one of them. One is full spectrum. So the question is, can we use one pipeline system to support all the steps that we want to do? One is interoperation. Downstream tasks often want to use the result from previous tasks, so that we want interoperation to be possible, enabled by this pipeline system. For example, we want to use the sentiment analysis results in the answer selection step. The property of pipeline system is customization. Can we freely change operation in a pipeline? For example, plug in a tokenizer, replace the translator, or remove the lemmatization. Another good property of pipeline system is to support flexible and easy model building. The question is, can we directly reuse a model for a new task quickly? For example, can we apply LSTM-CRF or 2 different tasks such as name entity recognition and POS tagging? Another very good property of pipeline system is to support different data formats. For example, in NLP, we want to support the result of dependency parsing, syntax analysis, or morphology analysis. So now our problem is to convert a complex pipeline on the left to a clean linear pipeline on the right. How can we do that? Our answer is to standardize NLP. To standardize NLP interfaces, we need to know a couple of concepts first. First of all, each processor in the NLP pipeline is composed of input, an output, and a model in between. And then the output will be served as the input in the next step. This is what we call the operationalized view. The conceptual view of this is more like a pyramid. The data is the supporting part for models, and models and data jointly support the task application. So what we really want to do is to standardize the interfaces between these 3 levels: task, model, and data. First, let's talk about data. The goal is to achieve versatile data support. One special thing about NLP data is the granularity. NLP data have many different granularities, such as character, token, sentence, document, or even corpus level. So, in our data representation design, we want the representation should be able to handle flexible granularities. Next, let's talk about data structures. Note that the data structure we are going to cover here are the NLP analysis results, not the raw text. So as a human, if we read the book, we would do some sort of analysis as well. We might use a highlighter to highlight important parts, or we might use a pen to draw links between them. So this analysis helps us to understand the text better. NLP systems can do very similar things. So let's again look at all the tasks we covered at the beginning of the tutorial. Have you observed any patterns on the output structure of these tasks? In fact, we can actually classify the tasks based on their output structure, such as a sequence structure on tasks, entity recognition, stemming. We can also have many different types of tree structures, such as syntax parsing or discourse parsing. Finally, we also have the cluster structure for tasks like entity correction. To put it in a simple way, the structures are basically spans of text, or links between objects, or groups of objects. These three types are actually very central in NLP analysis. Let's talk about them one by one. Let's first look at spans. Spans are essentially pieces of text that have a certain type. More formally, we can define a span as a tuple of a type, a begin of set, and an end of set. Of course, we can have some additional fields to store more information about a span. Here we show two examples. The first one is an entity mention from character begin at 25 and ended in 35. Another span is a predicate. It starts at 42 and ends at 46. Span representation is very simple. It's a powerful representation that can help us represent many NLP results. The next very important data structure is link. Link is essentially a typed connection between two objects. Formally, we can define links as a tuple of type, parent node, and a child node. Link can also have additional fields to represent more information of this link. In this example, we see a semantic row link that links the predicate and entity mention. This represents that the entity mention is actually a participant of this predicate event. Finally, we have groups. A group is a type and a collection of objects. Formally, we can define it as a tuple of the type and the member list. In this example, we're showing an entity coreference group which contains two members, adding cooks and cooks. This group represents that these two entity mentions are referring to the same entity. What we have done so far is creating three basic types of NLP analysis results: span, link, and group. We can further divide this type into more fine-grained types. For example, we can use a token type to represent a word, or use an entity mention type to represent entity mention. We can further inject domain knowledge into this tree. For example, we can create a medical entity type under entity mention to represent only those medical entities. This tree is called ontology. Organize the data structure as an ontology tree. Ontology can be customized for new domains. And with ontology, we can fully define all the analysis results that we want in this domain. Before concluding this session, there are several practical considerations in handling and representing data. First is serialization and deserialization. The minimum requirement here is that serialization and deserialization should be lossless so that we can pass them around on network channels. Also, I want our system to be able to easily batch or catch this data. This is very important in the deep learning area. Further, we might want the data representation to be readable or interpretable, not only to machines, but also to humans, so that we can easily inspect what happened in the data. Finally, we might store a lot of metadata in our data representation, such as the source information or the data creation time, etc. So what we really hope here is that the backend system can help us automatically store this meta information. And finally, there's one type of data that we haven't talked about in the previous session, which is global data. In the NLP system, we have a lot of global data to deal with, such as vocabulary or embeddings. We won't go into detail about these global data. Keep in mind that we have to handle them as well. Okay, after data, let's talk about tasks. How do we represent tasks in NLP pipelines? We'll show you the design, and here keep in mind that we want to achieve 3 good properties for tasks in NLP pipeline, which includes full spectrum, interoperation, and easy customization. Between tasks, we can actually use data as the interface. We can define a standard interface using the ontology we just covered. This can help us achieve task modularization, because now each task understands each other through the ontology. However, each task only needs to concern about its own ontology nodes. Then each task can access the data using the granularity and structure provided this ontology. This piece of pseudocode, you can see that we might be able to get all the predicate mentions and entity mentions in terms of the granularity of sentence. Let me show you how this is achieved. In fact, with the standardized data and interfaces, tasks are already being organized in a very modular way. In this example, you can see that each task processor is actually only adding one type of ontology node into the data frame. For example, tokenizer is only adding tokens to the data frame, and NER is only adding entity mentions into the data frame. What's happening under the hood is that tokenizer will get all the sentences from the data frame, will analyze it, and write back a list of tokens to the data frame. You can see that all this analysis result pass on so that the next processor can access any of the previous analysis results. And that next processor can understand the language of the previous analysis because we are using a shared ontology. Let's make sure input and output steps are standardized. This pipeline design helps us achieve two more properties. First is customization. You can now easily insert or replace a task processor from or to the pipeline. Secondly, interoperation is also achievable because now each task can access the analysis results of all the previous tasks. For example, information retrieval engine at the very end can see all the name entities, the tokens, and wiki entities. You can build complex queries here to do good retrieval. Now, let's move on to standardized models. In this session, we want to achieve is to have flexible model building ability in this NLP system. As we have covered before, a model is a transformation from input to output. In this example, input is a sentence with both entity mention and predicate mention highlighted. And the output is a tree structure of the predicate and entity mentions. This is the task of semantic parsing. Let's go into the detail of this model. From the input side, the model needs to get the data from the sentence, including the predicate mention and entity mention. On the output side, what we need to do is to write out the model output, which are the predicate links. From here, you can see that we already have a standard interface between the data and the model, which is the ontology language. So, I want to ask, how can this model data structure help us? What the model data interface actually do is to separate the task structure from model structure, and then use the data as an interface in the middle to connect the task structure and the model structure. For example, if I have an LSTM model, and we have the task of POS tagging, what we need to do is to use the data interface, select all the tokens, and return all their POS tag for the LSTM to train. Similarly, changing very few parameters can support a different task using the same model. For example, if we replace the POS tag with an NER tag, and we can run the LSTM on this name entity recognition task.
Before concluding this part, here are some other handy model support that a good NLP system may provide. For example, a built-in feature extraction system can be very helpful. This is actually not difficult by using the deep neural networks, which are considered to be universal function approximators. With a feature extractor, we may also want to have the training support. A training loop in the actual production environment is quite different from the lab setting. You don't have nicely pre-processed data. You may need to handle online stream data or do data batching or unknown sizes of data. Now the system should be able to help you abstract away these complex data preprocessing and then interfacing with the underlying learning framework. This comes to our next bullet point, that there should be an easy-to-use learning library interface provided by the NLP system.
In this section, we haven't covered the model details, such as architecture choices. In fact, in NLP, we have a rich family of architectures. We will cover some of them in the second part of this tutorial. So far, we have briefly covered how to standardize an NLP pipeline. We cover 5 properties of a good NLP pipeline, such as full spectrum support, where a pipeline can do many different tasks. Secondly, whether we can achieve interoperation between these tasks. Then whether the pipeline can be easily customized, whether the pipeline support flexible model building, whether pipelines support different type of data structure. What we have covered so far are quite abstract. Let's now cover some coding. The next section is the case study of how to modularize NLP pipeline with a tool called Forte.
Forte is a flexible and powerful NLP pipeline built by us. We build Forte to validate all the ideas, such as universal data flow, customizable pipeline construction, a full spectrum NLP pipeline. Forte actually includes information retrieval components, task analysis components, and task generation components. Forte also supports abstract data, model, and task interfaces, similarly to what we have just covered. Forte also supports other features, such as batching and automatically bookkeeping.
Consider Forte more as a scaffold of NLP technology instead of a toolkit for NLP research. Forte is designed to be an open and flexible scaffold for NLP. The whole thing is supported by data representation. On top of that, we have ML libraries, such as Tessa or PyTorch, to do machine learning and deep learning. On top of that, we also support pre-trained models, such as Hugging Face. Then, Forte supports a wide range of NLP technologies, using models such as LSTM, or third-party softwares such as Nlp. And on top of that, Forte tries to help you build domain knowledge with the ontology system. What Forte is doing is to help standardize NLP and bring NLP technology to a particular domain, such as the medical domain mentioned at the beginning of the tutorial. Let's again use the running example to explain how Forte can do this. Let's revisit the problem. A German-speaking user wants to find good actors, however, we only have a corpus of English movie reviews. How can we help him? What Forte allows you to do is to chain lists of processors in a linear manner very easily.
Forte implements the linear pipeline construction with very straightforward API. This is a piece of the actual code of Forte. It demonstrates the pipeline construction can be done via a very simple API. Here, we first initialize the pipeline object. We then set the reader to the pipeline. A reader is the entry point to the system, where external data can be converted to the internal data format. Now we simply need to add the processor to it.
Now let's look at the actual implementation of some of these processors. Let's start with the query creator. Here, let's create a simple text-based query using Elasticsearch. All you need to implement is to return a query string in this format. So by building the simple query, Forte can help you automatically run the query in the backend on the Elasticsearch. Alternatively, we can create an embedding-based query. Interface to the build query function is still the same. You provide a text string. However, the return value becomes a NumPy array because what we are returning is an embedding. Inside this function, what you really need to implement is the bird embedding. Next, let's take a look at how we can implement a sentiment analyzer. We can easily wrap an external sentiment analysis into the system. Here, we use Vader sentiment as an example. This is very simple. In the process function, what you need to do is to get sentences and parse the sentence text to the analyzer. And then we just need to write back sentiment scores to the sentence. Lastly, let's look at how we can implement a translator. To get a translator, we will show you how they help you to add an external API. What we need to do here is to get the translated text from bin and then write back the translated result to the data. Forte is helping here that it stores all the analysis results from the previous steps. Given the user query, we can now select a response using incorporation. For example, we want the response to contain actors. Now we can use NER and entity linking to help us. Then, if we want to select a response with positive sentiment, we can use Sentiment Analyzer to help us. The response creation time is all the previous stored analysis results and make informed decisions. Here are some take-home messages of the first part. If we are designing an NLP system, make sure to use standardized and shared data representation. Note that NLP concepts can be categorized into an ontology tree. Using such categorization, standardization can be made much more easy. When we are processing the data, what we really want is to enrich the data. We don't really want to delete anything. Next, we want to keep consistency interface between models and tasks. And last but not least, you have to understand the domain to design a good NLP interface and a good NLP ontology.
Hi, I'm Zecong Hu. I'm a graduate student and research assistant at Carnegie Mellon University. I'll talk about how to modularize NLP modeling and learning procedures, leading to what we call Composable ML. The field of machine learning is growing rapidly, with more people entering the field and new technologies coming up every day. For ML researchers, there's ever so much to learn, to implement, and to try out in our own research projects. If you've ever built a real-world machine learning application, not by downloading an existing piece of software, but by building it from the ground up, you have probably experienced the same thing, digesting pages and pages of papers and equations, and learning all kinds of tricks. This is time-consuming. But machine learning algorithms are not that different from each other. By analyzing use cases, we can find common patterns and identify reusable components, which leads us to Composable ML. Basically, Composable ML is to provide as building blocks the basic components needed for implementing an ML algorithm. With Composable ML, one can build ML models more easily by plugging in and swapping out blocks, and relieve the burden of writing boilerplate code again and again. Machine learning is broadly defined as the computational methods that enable machines to learn concepts and improve performance from experience. Thanks to the mathematical first principles that lie beneath the equations powering all these different machine learning innovations, there indeed exist very systematic structures of ML algorithms, which can be decomposed into a set of basic building blocks, including architecture, loss, constraint, learning procedure, and experience, which is data. For a quick overview of the key components, we can write down a super simplified representation of a machine learning solution, which is shown in this function. We also give examples of each component under an image classification task setting. Theta here represents the model architecture, including parameters and the topology of the model. The model architecture also largely defines its inference procedure. For example, inference in a feed-forward network is basically the forward pass. In image classification, the most used architecture is convolutional neural networks, followed by a dense layer, which is essentially the underlying architecture for popular models like ResNet and BGG. E is the experience, which is often a set of data examples of pairs x and y on which the model is learned. In image classification, x would be the image and y would be its label. L defines the loss function. The loss function is what we aim to minimize during learning. It helps to drive the goal of the training. In image classification, the loss function is usually the cross-entropy loss of a predicted label distribution of the image versus the ground truth label. More complicated models may incorporate additional loss terms that could serve as further guidance for model training. Omega is the constraint, which augments the loss function, adding restrictions to the model parameters. For example, although they are not commonly seen in large-scale models, L1 and L2 regularization is a common form of constraints which encourages model parameters to be sparse, which means that the parameters will contain more zeros or smaller values. Finally, the minimization algorithm defines a learning procedure. The algorithm is responsible for optimizing model parameters so that the loss function value decreases. After taking a high-level view at the components in the generic sense, let's now take a closer look into each of the components, specifically in the text domain. Take machine translation as an example, where we're given sentences in one language and need to generate translations in another language, in this case, from English to German. We will be looking into the model and training parts, which is the core of our application. Let's first take a look at the different choices of model architecture. A very basic architecture in the text domain, especially in text generation tasks, is the language model, or LM. Assume we're giving a sentence Y, which consists of a sequence of tokens, Y1 through YT. A language model computes the probability of a sentence by decomposing across the time steps. The distribution of each token at time t is conditioned on all of the previous tokens. For example, the probability of generating I like this is the probability of generating I multiplied by the probability of generating like, given that I've already generated I, and that multiplied by the probability of generating this, given that I've already generated I and like. A good language model should accurately predict the distribution of the next word, given the previously generated words. So this kind of decomposition allows us to generate a sentence from left to right. A popular implementation of the language model is LSTM-RNN, which I'm sure everyone has heard of before. It takes as input one token per time step and predicts the next token, while also keeping track of what has been generated in its hidden state vector. Another emergent and often state-of-the-art implementation is the transformer, which consists of a set of multi-head self-attention blocks. The language model allows us to generate sentences, but it is unconditional generation. Namely, it doesn't depend on any context. To use language models in actual tasks, it's often necessary to condition the language model to some input, or we call it context, so that one can generate text about the input. For example, in machine translation, we condition on the source sentence, which in this case is the English sentence, in order to generate the corresponding German translation. In medical image report generation, we condition on the medical image to generate the report about that image we condition on. Probabilities computed by conditional language model are conditioned on the context X at each time step, and the previous LM architecture, such as a transformer, now becomes a submodule called decoder. And we use an encoder to encode the input context into a feature vector, which is then fed into the decoder. So what we have now here is the encoder-decoder architecture, also known as sequence-to-sequence or sec-to-sec. Zooming out a bit, machine translation is just one task among the many possibilities in natural language processing applications. We chose to frame MT as a sequence-to-sequence problem and use an encoder and a decoder as the architecture. We can then look at other tasks on the horizon, for instance, sentiment analysis and named entity recognition, which is NER. Sentiment analysis takes a sentence as input and outputs the sentiment of the sentence, either it's positive or negative. So we frame it as a classification problem. NER requires finding phrases within a sentence that correspond to named entities, such as person names and geopolitical entities. We do so by labeling each word in the sentence as either within or outside of a named entity. This allows us to frame it as a sequence classification problem. And then we can go down to architecture choices. Classification tasks, of course, they require classifiers. And they also require encoders, which would encode the input sentence into vector representations and then feed it to the classifier. And as we go even deeper, models get more fine-grained. Let's look at the classifier. A classifier takes as input a vector and outputs the label distribution. So a feed-forward neural network would be fit for the job. We can use a feed-forward neural network to implement the classifier. For sequence classifiers, of course, we can also use feed-forward neural networks, but we can also impose restrictions on the sequence of labels that are generated, and that can be done using a CRF or an RNN. And as we previously mentioned, both RNNs and transformers are popular implementations for encoders and decoders. To further break it down, modules are composed of even finer-grained parts. A feed-forward neural network consists of multiple layers, including convolutional and dense layers. RNNs can use different cell implementations. Among the popular ones are LLCM and GRU and such. Attention is also widely used for sequential models. For instance, RNNs use recurrent attention modules, such as the Bucknell and Long attention. Now, these are named after researchers. And on the other hand, transformers use multi-headed self-attention. So far, what we get is the graph of architectural components, where one component can be reused in multiple higher-level components. Now, with the components, one can further compose many more complex architectures, such as the canonical encoder-decoder, sometimes with an attention. This is figure A. We also have the adversarial model that has an encoder, a decoder, and then a binary discriminator. That is the figure D. And we have the multitask learning scenario where there are multiple encoders and multiple decoders trained at the same time. This is figure E. Without a well-designed compositional framework, these variations will be hard to implement, and there will be a lot of code repetition. Now we've seen the examples of architectures and the breakdown and compositions. Let's visit loss, learning, and inference together, because they are closely interconnected and often referred to by a term that's badly overloaded, algorithm. We can often classify the learning procedure based on the form of supervision. When supervision is provided as data examples, we're given the expected output for each input, and the goal of the model is basically to generate output that matches the ground truth. This is often referred to as supervised learning, and common methods such as maximum likelihood estimation, MLE, fits into this category. But we don't always have access to such examples, and sometimes we don't know what the output should be, but we know how to evaluate an output. The evaluation result is probably not differentiable, but it can be used as a reward to optimize the model. And in this case, the reward is the supervision. Most reinforcement learning algorithms fall into this category, including policy gradient and actor-critic algorithms. Yet another case falls somewhere between the previous two categories. We don't know the output, but we have this differentiable auxiliary model that we can use to critique it and to provide supervision through the backpropagated gradients. Most adversarial methods fall into this category. The first learning algorithm is MLE, which is basically the most popular algorithm. The learning goal is to maximize the log likelihood of the data, and this will increase the probability of the model predicting the correct label, Y star, given the input X star. The loss function that we use is negative data log likelihood, also known as the cross-entropy loss. Since our objective is a maximization objective, we use the negative as the loss function, which is something that we should minimize. And in this learning algorithm, the inference procedure, which is the procedure to generate a sample, is like this. For every time step t, we feed in all the previous ground truth tokens to decode the next step. The equation form will be like this. This inference procedure is called teacher forcing decoding. The second learning algorithm is the policy gradient algorithm used in reinforcement learning. The learning goal is to optimize the expected task reward, such as the BLUE metric for machine translation, which computes phrase overlaps. The standard policy gradient algorithm uses the negative expected reward as the loss function, as shown here on the slides. But there are also variants of the loss function. For example, we can augment the loss with a baseline by subtracting the baseline evaluation from the reward, and this helps reducing the variance. The inference procedure is different from that of MLE in that we don't rely on the ground truth. Many decoding algorithms can be used here. For instance, we can use greedy decoding, where at each time step, we pick the prediction with the highest probability. We can also use beam search decoding, where we would explore all the options at each time step and only keep track of those that are top ranking. The third learning algorithm that is increasingly popular nowadays is adversarial learning. In the learning procedure, we train a discriminator to distinguish between real data examples and fake examples that are generated by our model. And the model is trained in the other way. It is trained to fool the discriminator. And as you can see, we have two loss functions here, one for the discriminator and one for the generator. The loss for the discriminator is usually the binary cross-entropy loss with respect to the real or fake label. The generator can use a number of different losses. There's the binary adversarial loss. The generator is trained to make the discriminator classify its samples as the real data. There's also the feature matching adversarial loss, where the generator is trained so that the discriminator's feature vectors on both the real data and the fake generated data are close to each other. A challenge for the inference procedure is that the whole process has to be differentiable. Otherwise, the gradients with respect to the decoder cannot be backpropagated using the chain rule. However, many operations are not differentiable, such as the argmax operation in greedy decoding or the sampling operation in sampling decoding. But there are ways to approximate those operations. For argmax, we can approximate it by using the expected value of a very peaky distribution, such as the softmax distribution of a temperature. For sampling, we can somehow magically convert it into argmax by adding an independent noise sampled from the unit Gumbel distribution. And combining these together, we get a fully differentiable approximation of what was the sampling decoding algorithm. This inference method is thus called the Gumbel softmax decoding algorithm. So up until now, we have seen examples of loss, learning, and inference. Indeed, there are even more learning algorithms available, such as a combination of adversarial and reinforcement learning, learning with structured supervisions, reward-augmented maximum likelihood learning, and so on and so forth. And it is the same with inference and loss. And finally, let us talk about the constraints. First of all, regularization is a form of constraint. When we add regularization to a model, what we're doing is adding this additional penalty form to the original loss function. Here, L is the regular loss, for instance, a cross-entropy loss, and omega is the regularization term. There are many forms of regularization, such as the L1 or L2 regularization, which adds a sparsity constraint that encourages model parameters to be sparse. There's also the KL divergence regularization, which pulls parameters closer to some prior distribution. And perhaps more interesting is another form that uses logic rules as constraints. It allows using structured knowledge as constraint to impose human prior knowledge and intent. For example, in the task of sentiment classification, we have very rich linguistic knowledge about what determines the sentiment of a sentence. For instance, given a sentence, food was good, but the service was very disappointing. We know the rule that if the sentence has a structure A but B, then the sentiment of B would dominate the entire sentence. We can form the logic rule as a constraint function, which takes a sentence and its label and returns the truth value of the logic rule. Here, if X, the sentence, is of structure A but B, and if Y, the sentiment, is the same as the sentiment of B, we would have a truth value of 1. Otherwise, we would have a truth value of 0. This fits in a framework called Posterior Regularization, which puts a constraint on the posterior distribution of Y conditioned on X. The general idea is to formulate logic rules as real-value functions, indicating how well the data pair XY fits the rule. A model that abides such logic rules should have higher values for F on more data pairs, which means that the expected value of F given X and Y under the posterior distribution would be higher. We're not going to dive into the theoretical derivations. If you're interested, check out these references. Now we've introduced common approaches in each component. What does a practical machine learning application look like? It looks like this. Many of these methods can be used together. For example, decoders with all these different architectures can perform these various inference procedures and use different learning procedures and different losses. As we can see, there is a large number of combinations of learning, inference, and architecture. We can't possibly enumerate all of them, so it is necessary to properly decouple them with clear interfaces. And this is the rationale behind our NLP library, Texar. All the architectures would expose a uniform interface for specifying any inference procedure. A learning algorithm will repeatedly call the specified inference procedure as a subroutine during training. The learning algorithm is totally agnostic to the model architecture, and they are properly decoupled. Now, let's see how we can implement an application in Texar. Let's try to build the English to German machine translation system we've talked about before. We now build our empty model with Texar. The first step is to load the data and do necessary pre-processing. With Texar, it suffices with 2 lines of code. The data module automatically does many standardized processing for you according to this configuration dictionary specified by the user. For instance, it does truncation, given that the maximum sequence length is 100, and it adds special anchor tokens like the beginning of sequence and the end of sequence. And it also does shuffling and batching. The data iterator would return an iterator over the whole dataset that returns 1 mini batch of data at a time. Now the dataset is ready to be used. We then build our MT model by defining a class. In this class, we first build a word embedder to embed the discrete text tokens into continuous word embeddings. Again, the user can provide a configuration dictionary to specify the hyperparameters. And then we build the encoders and decoders. The encoder encodes the word embeddings into higher level feature vectors. Here we use a transformer encoder. Now, with the consistent Texar interface, you can easily change the architecture, for instance, by swapping it with a bidirectional RNN encoder or a BERT encoder. And similarly, we can define a decoder using hyperparameters. We also specify that the decoder uses the same embedder that we use for the encoder. Okay, now that we've built the 2 modules, we can now move on to the forward pass. First, we encode the source text. Data from the mini batch can be accessed through this batch dictionary. We can access the indices for words in the source language through the source text IDs entry, and the sentence lengths through the source length entry. We first embed the indices with the embedder by calling the embedder with the data we have from the batch entry. And then the embedded results are fed into the encoder by calling the encoder with arguments. We can see that the whole API provided by Texar is very clean and concise. We then move on to the decoding part. Here, we will use teacher forcing decoding in order to do maximum likelihood estimation for the model. To do this, we set the decoding strategy to train greedy. This is just Texar terminology for teacher forcing in training mode. And then we feed in all the other factors that are needed for this decoding strategy, including the ground truth text IDs. Here it is target text IDs, and also the lengths. We also feed in the encoded source feature, which is the enc output variable here, and feed it to the decoder as a memory so that the decoder can attend to the memory during decoding. With all the infer results ready, we can now compute the loss, which we will minimize during training. Now, recall that for MLE, the loss function we use is cross-entropy loss. Texar provides a bunch of easy-to-use APIs that are tailored for sequence-level training, such as the sequence sparse submax cross-entropy that we use here. What we need to do is we input the ground truth labels and the logits by the decoder's teacher forcing decoding inference, and then we can just get the loss. So up until now, we have the data, the model architecture, the inference, and the loss functions. Due to time limitation, we will omit the training loop, which is basically using SGD optimization to minimize the loss. What is worth mentioning here is that Texar PyTorch provides an executor module, which handles the entire training procedure, so you don't need to write the boilerplate training loop ever again. So this is the part where we use MLE, which involves teacher forcing decoding and the cross-entropy loss. You might wonder, how easy would it be to switch to another learning algorithm? And the answer is pretty easy. To switch to another learning algorithm, one only has to change the small portion of relevant code, which is outlined here in the red box, while keeping all the other parts like data and model architecture untouched. To give an example, here we try to switch from MLE to reinforcement learning. In reinforcement learning, we can no longer use teacher-forced decoding because we don't have the ground truth output. So here, we choose sampling decoding. To do this, we first set decoding strategy to infer sample. And then we feed in the additional factors that are needed for this decoding strategy, which includes the starting tokens and the end tokens. Texar then provides a sequence policy gradient agent called secpg agent that handles everything else. So the user only needs to make minimal modifications to their training loop. They should just get a sample from the model, evaluate the reward, which is blue score for machine translation, and then just feed it back to the agent. Everything else is taken care of. Now, what if we want to switch to adversarial learning? First of all, we need an additional component, which is the discriminator. So here we construct a 1D convolutional classifier as our discriminator. Now, we need yet another inference procedure, which is gumbo submax decoding. Since this procedure, we consider it to be quite a bit advanced, and usually only for ML expert users, Texar provides a more customizable API, which is based on helpers. So the user will create a gumbo submax embedding helper, and then plug that into the decoder. And finally, we evaluate the adversarial loss by calling the binary adversarial losses function while passing in our discriminator. From these examples, we can see that although the learning methods are vastly different, users can make minimal changes to their code thanks to the unified interfaces that Texar provides. Up until now, we've been focusing on designing the model and defining losses and constraints. From the aspect of a deep learning library, what we have done so far is basically constructing a computational graph, be it a static one or a dynamic one. But that is only part of the story. There's another important part, which is training. So training is defined as using gradient-based methods to optimize model parameters. For neural networks, the most common approach is stochastic gradient descent, or maybe some variant of it like Adam. These methods are compute intensive, and modern DL frameworks would make use of GPUs to speed up training. However, sometimes we still find that our GPUs are not fully utilized, and I'm sure people are familiar with something like this figure, and it's painful to see. So you are using GPU tensor operations, and you're pretty sure that your model is compute intensive. But why do we have the low utilization here? And this is actually quite a common problem in research code, and often there are three underlying issues. First of all, there's often a bunch of pre-processing tasks that is performed at the start of a program, such as reading from the disk, performing tokenization, and maybe converting tokens into IDs. Often the pre-processing tasks is done for the entire dataset, and only after that do we proceed to construct models and creating batches. And this would lead to a long startup time for each round of the program, as illustrated here with the green segment. The second issue is that data processing is usually performed on CPU, while the multi computations are done on GPU. So it is perfectly possible to have both run in parallel. But a lot of research code is written in a single process fashion. As we see here, the red segments that correspond to data processing and the blue segments that correspond to multi computations do not overlap at all. The third issue is that data is synchronously moved from CPU memory to GPU memory. In most of the PyTorch code that I've seen, data is passed directly into the model forward method as a CPU tensor, and only then are the data moved to GPU by manually calling tensor.cuda. As we see here in the brown segments, movement of the data does not overlap with either processing or the computations. A side note here is that these definitely aren't all the issues that are bothering with low utilization, but I think they are representative of some of the most ignored ones. And the solutions to each of these problems are rather simple. First of all, we don't have to preprocess the entire dataset at the beginning, and we can just lazily preprocess each data example as we construct the batches, basically construct them on the fly. As we can see here in the figure, we split up the long green segment into smaller segments and do them just before processing. For the second non-overlapping issue, we can perform data processing on a separate process, or even on a bunch of separate worker processes, so that they can be executed in parallel with model computations. We can also do pre-patching, which means that we prepare the next few batches of data while we were computing the current batch on the GPU. This increases the overlap between CPU and GPU compute. And finally, on the issue of data movement, one thing that we can do is asynchronous copies. And this is surprisingly simple in PyTorch. You can just call pin memory to first move the tensor to a shared piece of CPU memory, and then call tensor.to with non-blocking set to true. These are I/O-intensive operations, so we can move them to a separate thread, and it doesn't occupy the CPU used for data processing. Now, the question is, if solutions are so simple, why do people still encounter issues of such low GPU utilization? And I would say it is because even though they're simple, people are not aware of them. A systems engineer might know how to avoid these issues, but a researcher might not. And that is where training abstractions come into play. Ideally, researchers should not have to worry about any of this. They can just write normal data processing code, and the abstraction should take care of all of these. And that is the rationale behind the design for Texer data modules. We provide built-in modules for common data formats, and we also provide customizable processing routines with guaranteed best practices. All you need to do is inherit from the dataset base class and implement 3 parts. First of all, the init method, which defines the data source and other required resources like the vocabulary. The process method, which processes a single data example. And what we do here is tokenization and mapping tokens to vocabulary IDs. And this would correspond to the green segment in the timeline chart that we've seen before. And finally, the collate method, which creates batches out of processed examples. And this corresponds to the red segment in the timeline chart. Now, let's see how these would work in action. The data processing behavior of the custom data class can be easily configured through configuration dictionaries. And here we showcase 3 different use cases. First of all, we do eager loading and use a single processing worker. The entire dataset is preprocessed at the beginning, but we see that batching is performed in a separate process and data movement is asynchronous. And this is what you get out of the box with Texer. The second case is lazy loading with a single processing worker. And this is exactly the same figure as we see on the previous slides, where we load and preprocess data only for the current batch. And the final case here is lazy loading with 2 worker processes. Here we make better use of multi-core processors and use 2 processes to create 2 batches in parallel. So in this example, it doesn't bring us much benefit compared to the single process case because processing time for a single batch is relatively short compared to the model computation. However, it would be useful in situations where data processing itself is time-consuming. For instance, if we're dealing with audio and need to extract features using some additional framework. So to summarize, the Texer library provides highly modularized programming by properly decoupling all the different modules, including data, architecture, loss, and inference. And you can easily switch between learning algorithms by only changing the codes that's relevant to the learning procedure. And finally, it provides data module abstractions that ensure best practices in data processing. What's more is that Texer has 2 versions, one that supports TensorFlow and another one that supports PyTorch. Both libraries have almost the same interfaces, so that you don't need to learn 2 sets of APIs in order to work with different libraries. So make sure to check it out if you have to use 2 different underlying libraries and want this one framework to work with them all. And finally, the take-home message for Composable ML. How do we design a Composable ML framework? First of all, you must think about all the different use cases that you wish to apply your framework to. This is probably the most important step because it makes you think about what functionalities you should support or emphasize in your framework. Then, you should identify the common structures in your use cases and group them into categories. These categories can form a hierarchy. For instance, in Texer, we have architecture, learning, and loss at the top level. And within architecture, we have encoders, decoders, and such. And levels beyond that, we have more fine-grained modules, such as the transformer encoder and the LCM cell. Finally, you should design a unified interface to allow easily swapping modules in and out. This will largely determine whether users will want to use your framework, because Even a well-designed hierarchy wouldn't be very useful if the user had to manually wire the modules together in complicated ways. By following these points, you're on track to designing a composable ML framework that best suits your needs.
Here, let's show you a very simple chatbot demo. This chatbot is very similar to the tutorial running example, where the user will enter a query in German, then use the bin API to translate it back to English. Now we can use the English query to retrieve some responses in our English corpus, and then translate back to German. This is the final result. Note that we can use many NLP toolkits to analyze English query. For example, here we can analyze the semantic rows of the query. As we have shown before, some of this analysis can help us more informed decision in the final response. Now, let's come to the conclusion of the tutorial. In this tutorial, we first gave an overview of natural language processing. We then show you how to modularize NLP pipeline on certain applications. Then further going to a model, show you how to modularize NLP models in a way of composable ML. We are still actively developing Forte and Tessa. In the future, we want to provide better data manipulation, such as data augmentation, data visualization, or even multimodal data manipulation, such as text and images. We further want to improve our interoperation by incorporating techniques such as joint learning and joint inference. We also want to try out automation of ML workflow, such as automate model composition and model learning. Thank you for listening our tutorial. This is the end of the whole tutorial. If you are interested in our methodology or our software such as Forte and Tessa, you can visit our project links. Our website is asyml.io, and from there you can find all the projects that we are actively developing.